Yes. Okay, here we go. We're managing our time towards finishing this problem, hopefully. And this problem started on the last video. I thought I hit Control All. There we go. Get it underneath all the detritus. Does the rate determining step, which we determined was Prop 2, that's why I copied it over here, early or late transition state. Okay, so yeah, did we establish endo or exo? I forgot. It's exo, delta H P2 equals, what was it, -9? Is that right?
Yeah.
And you don't need this diagram to answer this question, but that's exo, right? So I got my exo, reactants start high and end low. And don't look at my hands, look at the screen, but it's very hard because it's so small. Anyway, yeah, that means the transition stays close to my reactant side, my left hand. That's be called early if you're on reactant side, right? Okay, so you're gonna write all of that down. And you got to acknowledge you're talking about energy allowing you to predict how something will look. That's not a normal connection. So you got to acknowledge you're doing that as your criteria. In an exo, this is part E again, thermic reaction, the energy of the TS, and I defined it at the top of the page while you weren't looking. The energy of the TS is closer to the energy. Notice you haven't talked about how the molecules appear yet, of the reactant. So the TS should appear to look like energy reactants more than products. And what would you call that if you're looking like the beginning and not the end? I need to see the word early for a point. Early. Early bird. This early bird's going to get the word. Yeah, just for that sentence, right? It's a lot. And then the diagram, 3 more, right? Diagram transition states. Yeah, with the square box. Telephone pole. This time the transitioning atom is not a hydrogen, is it? Which atom's moving from one place to another? Br. And early on, Br is real close to Cl, right? So if you put your Cl over here, you can put your Br close and say this. What is that? Oh, I didn't even mention in the other video. What does the dots mean? Partial bond. And in an early transition state, they're real close to where they began, which was chlorine. I know you get left to right messing with your brain now. You could have written this the other direction. As long as Cl is closer to Br, then you have the right answer. If Br is closer to the carbon, you have the wrong answer. And the carbon is the carbon here, and it goes down in there, and then it goes up here to a double bond, and it goes here. There you go. So that's your 3 points just right there. Real close to Cl, like it was in the beginning, early. And there you go. And then the easiest new stuff, you won't be upset that I'm going to throw these new things in there. These are the simplest things and the fastest points on the test. To do a termination step, 2 radicals meet. This is not a good scenario. It's something we need to avoid, but it happens if you're not careful in these reactions. So you've got radicals on the page, Previous page, you had a Br and a Cl and a carbon radical. Pick any two of those, hook them up directly. So F, no, that was F. G. You want to do Cl? Oh, make your life real easy. If two Cl's meet, they hook up like this. It looks like initiation, the opposite. Hey, what's a good word for the opposite of initiation? Termination. Yeah, you killed initiation here. Like turning the light off. And that's G. H is easy. Which propagation step required chlorine radical? Go back, it wasn't prop 2 because I don't see it. Which propagation step requires chlorine radical? Prop 1. What happens if chlorine radical is no longer there? Can you do propagation step 1? No. So if you're using up chlorine radicals like you just did, you killed prop 1. Hey, use those words literally. Termination. What? If you're terminating people, you're killing them, right? Okay, bad analogy, but killed prop 1. That's the answer to why it's a bad thing. Explain why termination steps are to be avoided. Why they are bad things. Why? Because you killed one of your propagation steps. Yeah. Let's do this radical, the other radical. Meeting itself or oh, the worst of the worst. Chlorine radical. Oh no. Oh no. Oh. Oh, and I didn't copy my molecule fully, did I? Yeah, there we go. We got a Cl. You're saying, hey, Dr. Whitaker, why are you so upset? That's the, oh, that looks like one of the products, but it's not the right one, is it? Even if it was a Br dot doing this, you're in big trouble. It's worse than this one. Answer to H, there's your second termination step. Here's your second explanation. It killed the prop step that required Cl radical. That's prop 1. It killed the prop step that requires the carbon radical. That's the one at the top of the screen. You see it? Carbon radical reacting in the way it's supposed to. If you're reacting it this way, it's not reacting the way it's supposed to. You killed prop 2. Terrible. So clearly we have a problem. Those termination steps. Can I explain why termination steps are to be avoided? Well, because we want to not kill our propagation steps. I guess that's implied here, right? And I explain how to do it. That's easy. Here's the only one where I can guarantee 2 points on a test for copying this sentence every time. Well, but before we have the 2 points given to you, when are two radicals going to meet? Are you going to have two radicals meet if there's one radical way over there and another one over there? Or are you going to have two radicals meet if there's 8 billion radicals floating around here of type A and 8 billion radicals of type B? Which one's going to have a better chance for radicals meeting? The more. So if you have a higher concentration of radicals, there's a better chance for them to meet. That's not just chemistry, that's life. Right? Okay, so there you go. Keep radical concentrations low. Because remember, in both both propagation steps, a radical needs to react with a non-radical. So if I have a radical surrounded by non-radicals, I'm going to get what I want. If I have a radical with radicals, that's going to happen faster than it's back. So keep radical concentrations low by, here's how you do it. Here's the lab part. Minimizing. Now, this one, the translation doesn't work a lot for my foreign students. So I'm trying slightly different wording, minimizing the amount of time that delta is used. It's literally turn the oven on only for a short amount of time, or turn the light on only for a certain amount of time, depending on if this reaction requires light or heat. Okay, and in this one I knew it was heat because at the top of the page it said delta. That's heat, which is just one form of H nu. It's called infrared if you're curious. So that's your guaranteed 2 points there. Please just, if I see that written on a piece of paper snuck under the test day, I'm gonna blow up. Okay. You guys are beyond that, I hope. Okay. And I think, did we do everything? Yeah, I think we're done. Make sure we got everything. Yep. Keep radical concentrations low by minimizing the amount of time that delta is used. That's delta. I want it to be ultra clear. We use delta for mass here too. Heat or light. That's what that delta means. Okay, now I'm happy.